middle of part 3, filtering. And I covered spatial filtering, and I've got in the beginning of temporal filtering. So I went through this. I'm going to skip over the spatial filters. Although you may remember this idea of triangulation, that was very important. Let me just say that a little bit. Remember that when we have a bunch of sensors producing observations all at the same time, then we just look at the intersection of the pre-images to obtain a filter, a spatial filter, or a triangulation method. I gave some examples of that, and we talked about disturbances and other things, and we went into temporal filters. You might remember this example that we did last time, right? Where we had the point that moves around up in this planar graph along these edges, and then we only get to see this part, and we reasoned about the state. We reasoned about the set of possible states, and we also reasoned about the set of possible trajectories. Right? Remember, trajectories are time parameterized functions, right? They tell you at every time what the state is. So what's the set of possibilities after watching a boring one-dimensional animation, let's say, of a point moving back and forth. So that's what we looked at. The part I got to next, which I was just starting on, was what happens when we have discretely indexed histories. In other words, y tilde now is a sequence of observations. Right? So imagine we have a sequence of observations. They all come from the same sensor. They arrive incrementally. So we have to update our filter incrementally. And what we're going to have to do, now that these come discretely, is we have to model what happens to the state in between observations, right? So if you're playing, let's say, a visibility-based pursuit evasion, that many of you are familiar with, if I all of a sudden turn off the visibility sensor for 1 second and then turn it back on again, where might the evader be? Essentially anywhere, right? Until you turn your sensor back on, you only know that they're not in the place where you've seen. You lose all of your work. So for that model, you lose everything. That's the kind of model you need to make up. You need to specify what happens when you don't see everything. The visibility-based pursuit evasion looks more like a continuous sensor, which is like this one, right? Continuous time sensor, which is like this one. However, most people in robotics are familiar with, sorry for jumping around too much, most people in robotics are familiar with this kind of scenario where you get a discrete sequence of observations. Or I should just say a sequence of observations. The observations themselves may be continuous, that's fine. As I said, we have this information space. So we have, based on the previous information state, we get a new observation, and we need this function that calculates the next information state. That's what a filter is in this context. That's what a temporal filter is. It's temporal because it's taking past information here and a current observation and figuring out the next information state. So it's operating over time rather than over, let's say, the space. Right, so I gave that before, just redoing a bit to provide some continuity. I gave these generic examples, sensor feedback, stage counter, just providing the entire history or making a state estimator. So I gave those last time. And then we started thinking about state transition models. Right? As I said, we want motion models that describe the change between stages when there's no observations. We have to specify this when we make a temporal filter. It wasn't important in the case of spatial filtering because it happens at one instance, right? And, you know, if you have a stationary environment, like if you have no change in your state, then the spatial filtering ideas work even if your observations are not at the same time, right? Because nothing's changing. So you could imagine that we could also handle that case. But now that we have states that possibly move, we have to reason about what happens. So we need some kind of model. I believe I gave this last time. This looks just like a discrete version of a differential equation, if you like. If we did this in continuous time, it would look like this. Say x dot equals f of x, or in other words, dx dt equals f of x. That's called an autonomous system, right, in differential equations. So that's what this is, just a discrete version of that. It just basically says I can figure out what the next state is going to be given the current one. When you get down to the level of calculus, you cannot specify the next state because there's no next time, right? Because delta t has gone to 0 in the limit when we define derivatives. So that's why it's only the change in state that you can integrate. That's velocity of state. You can integrate that to get the over any time interval you want, right, to get where you're going to be. So that's how that looks, and then we end up with this nice thing called a forward projection, where it just says, all right, if I'm in a set xk, this is where I'm at the next stage, which is xk plus 1. I can get that expressed entirely in terms of xk, which is given here, and this f function, right, which is used right here. So I look at all the possible places where I could be coming from, and this will tell me all the possible places where I could be going to, right? So that's it. Questions about that? So I think that's where we stopped last time. Now I can introduce non-deterministic state transitions. So that could mean that given that the state is what it is right now, say it's given the state, where might it be in the future? Where might it be 1 second from now, if that's what the next stage means? It could be 1 second, or it could be until some sensing event occurs. So what we have is, let's say a mapping, I put it as capital F here, just to denote that it's a set value mapping, let's say. So based on the state, we get a set of possible next states. So that's what I'm saying here. So if I call it capital xk plus 1, capital F of xk, and it's some subset of the state space. So now I can still write the forward projection. The only difference is that there's element of here. It's the only difference. Right? We can look back at the other one. Here it says equals, because that's the way the equation works. But now this F is going to produce a set of next states. So it just goes like that. Capital F produces a set of next states. And that's all we really need to talk about this. So even if you know the state, you get a set of possible next states. If you have a set of current states, this gives you the set of next states. Right? So there's enough that's been defined. One example of this that we use is that the bodies must move on a continuous path. Or maybe we could say that the bodies, maybe like an invader, moves with no more than unit speed. Right? So if it moves with no more than unit speed, suppose, for example, maybe we have, maybe this is my set xk, and I say to you that, some disk here with radius r, suppose that's xk, and we're moving in a plane, and 1 second goes by, and I say that to get to the next stage, and I say we have bounded speed. Let's say you can move no faster than unit speed. So if you can move no faster than unit speed, then what's xk plus 1 going to be 1 second later? Just 2r, right? No, 2r or r plus 1? Unit speed, 1 second later. Yeah, so that's all that happens is we get a little bit bigger, well, or maybe a lot bigger, depends on r. We get a 1 here, right? So that's how you can imagine these things. You get like a kind of, just like the kind of expanding gas in the pursuit evasion problem. If I make bounded speed, I would get some kind of complicated geometric computations, right? These are called reachable sets. You may look at this kind of literature, reachable. People study these for control systems and dynamical systems all the time, and they're quite complicated to compute in general. Maybe for a simple bounded speed model, they're not too bad, but if you want to make a more complicated, say, differential equation that describes this expansion, it could be significantly difficult. It could be that you can only do it numerically. For this low of a dimension, you can do it quite nicely numerically, by the way. I can talk to people about that if you're interested. Right, so that's the idea there. We need some expression. Does that make sense? So if nobody's watching, there's some, let's say, expansion. I guess I didn't write what that bigger set is. That bigger set here, all of it is x k plus 1. The whole thing, including xk. In that particular case, xk is a subset of xk plus 1. It doesn't necessarily have to be that in general. We could also do things probabilistically. I could say there's a probability distribution over next state given the current state. So that's a standard way to represent Markov models, right? You have a Markov chain or Markov process. Using Markov chain is, I guess, the right way to express that. And given the state, right, it's Markovian, that's enough to be able to get the probability distribution over the next states. And then if I want to make a forward projection, it looks something like this. So if I have a probability distribution over the states now, right, in stage k, and I use that up there to do a summation, this is like just a weighted sum version of the previous stuff I covered, that will give you a probability distribution over the next states. Is that right? Does that make sense? Just marginalization. You can note very much similarity with this. Here we're getting a set of possible next states, but there's no probability weights on them, right? So the prior for this problem, it's not really a prior because we're just talking about sets, but the prior is big xk. It's just a set, right? And then we compute what looks like the posterior, which is big xk plus 1, and we use this function up here to do it. In the probabilistic case, the only difference is that all of the next states are weighted probabilistically, and the prior is weighted probabilistically. So this is how it looks. Is that okay? I think it's going to be very helpful to go back and forth between non-deterministic and probabilistic representations in your mind. It's nice to switch between them. And really it turns out that the probabilistic case just has more expressive power, you might say. It puts probability mass on the across the points, let's say. More formally, you have to define a measure space for that. Sometimes that's a problem. It may cause more difficulties, but that's conceptually at least the only difference between the two, between non-deterministic and probabilistic. Right. One more thing that happens, and the kind of filters that people talk about in robotics, is that we have to add actions. So actions are like, say, commands that we give to robots. They are the inputs of a control system if you have a control background. So actions or inputs doesn't matter. I think the word action shows up quite a bit in artificial intelligence literature and books and things as what the agent must choose, right? So I just wanted to put in actions. It turns out actions do not really complicate filters very much, except they complicate the notation. So what I hope, I'm going to show some notation. It'll be a little more complicated than the previous notation, but I would like you to think about it as, try to remember that it's not very different than the previous case. It just has an extra action in it somewhere, and it doesn't really matter very much in some sense. All right. First of all, when I introduce actions, these actions are going to affect the state transitions. So that's going to be the idea. So they affect the state transitions in some way. And there's two cases in the context of filtering. Maybe, or should I say in the context of filtering and planning more generally, maybe we do not get to choose the actions, we only receive them. That's the passive case. All right? So, in other words, the actions that are taken are just extra information. Like we are told that the robot was commanded to go forward. We are told that the robot was commanded to turn right. So we are told that particular command, that's written down as an action, and that's part of the information state. That's part of the information you have. If you know that, it should be more powerful than not knowing that, if you have a reasonable model set. The other case is active, where you actually get to choose the actions. You can make the set of next states, if you like, or the probability distribution over future states, depend on your actions, and you get to choose them. To me, that looks more like planning, and that'll be coming later in the course. But in either one of these cases, whether you get to be active or you just have to be passive, the filtering problem looks the same. So I just want to point that out. So filters are filters. You don't actually control anything when you make a filter. You're just gathering information and storing it, hopefully to make good decisions later, if that's the problem. Some filtering problems, you don't even make a decision. Maybe you're only trying to count the number of robots or bodies, people in a room, let's say. Maybe that's the task. So I guess the decision is only declaring what the number is. So it doesn't look like a planning problem so much. All right, so let's say let capital U be what's called the action space. So that's going to be the set of possible actions that you have. I could call it an action set, I guess. It's not a topological space or anything complicated usually. But it can be. It can be a part of Rn if you want, a subset of Rn, or it could be some discrete set. And then I'll say U sub k is the action that got applied at stage k. So we heard that, we learned that action UK got applied at stage k. That's now part of our information. It's almost like another kind of sensor was presented that reports an observation called UK. You could model it like that if you want, but I won't do that. That will maybe cause confusion. But it's like that. It's like another kind of observation. So when I have that, what I do is I take my previous models and I just add UK to all of them. So the predictable state transitions just has a UK here, and this is what we call a discrete time control system, right? If you've seen the control systems before, this one here is a discrete time control system. In the non-deterministic case, it looks like this, where, I don't know if you remember the previous one did not have u here. It just said x goes to the power set of x. Now we have u, so given the state and the action, we get a set of possible next states. And in the probabilistic case, we just put it on the other side here, on the conditional side. We get a u that we had. So in other words, this would be read as probability, a density of xk plus 1 given xk and uk. So all of the stuff I just presented for these three cases when we look at forward projections should look the same. Let's see if I have that coming. Let's see. So if I go back to the forward projections for these cases here, see when I did all of these, if I just put, for example, here a uk up there with the xk, and I put if I put that there, given uk, and I put given uk here, and I have, I'll say a little bit more. Let me stop on that. Let me come back to that. But I can go and put UKs in these, but I still want to do that a little bit later. I have to be careful. I'm going to make the full sort of general filter, but there is a little more complication to it, so I have to be careful. So I should go forward instead of backwards. Let me see. All right. So we have this information. We have these transition models now with these U's, and now when we make the information state, I want to expand it. So I want to say that we now have an action history in addition to an observation history. So up to now, we only had a sequence of observations that you get. Now we have a sequence of actions. This is everything that's been chosen, or let's say applied to a robot, if you want. Everything that's been commanded up to some current stage. And so now this phi function, it depends on the previous information state, the previous action, and the current sensor reading that comes. So what was commanded before, after the last information state, and what is the new sensed information that we have. So that's how it looks. The previous one only had this deleted, right? That's how the previous filter looks from yesterday and just a little bit earlier today. All right, so now the history information state is both of these, y tilde and u tilde. Y tilde is the history of all the observations from the sensor, and U tilde is the history of all of the actions. It'll often be written like this in kind of an annoying way, in that we have y tilde sub k, but we have y tilde sub k minus 1. That's because we're reasoning about the action that got applied before. Now we have an observation. If we apply uk, it takes us to the next stage. So we don't want to do that. So that's why it's off by 1. Very common situation in the control system. So I can make a very trivial kind of filter again. This is the kind of filter that does not remove any information at all. It keeps everything. And it does that by just doing this very simple transition. I take my entire history up there, A to k, k minus 1, I guess in this case, and I just take the new action and the new observation, and I just concatenate them on. Right? So when that filter transitions, let's see here, let me write it on the board here. So in this case, A to k, as I have there, is equal to, I wrote it with tildes. Let me write it without tildes just so you can see it a little better. It goes y1 up to yk, and u1 up to uk minus 1. Right? So that's really what that means up there. And all I'm saying is, if you come from the previous information state, previous one up here already, that's y1 going up to yk minus 1, and u1 going up to uk minus 2. So all you do to go from here to here is just concatenate on the newest information, pieces of information that you have, which is just including this and including this, right? So that's the simplest filter. It's kind of ridiculous. All it does is record everything for you. I gave that as one of the 4 examples last time. It's in some sense the most trivial filter, and it's kind of analogous to like the sensor that lives at the top of the sensor lattice. It's the most powerful. It doesn't lose any information at all. So it's important to keep that one just for perspective. All right, I'm now going to discuss 2 different generic kinds of filters that are temporal They fit this template that I've given, and they're going to work on two different spaces here, but they're quite related. So one of them is going to be called the non-deterministic filter, and the other is going to be called a probabilistic filter, or a Bayesian filter. I would say the second one is wildly popular in robotics. People are using these all over the place. I think the first one is significantly less popular, but the first one is significantly more related to computational geometry. So, I think there should be more use of the first kind, and I think that you can actually make Bayesian filters out of non-deterministic filters in very interesting ways that reveal a lot about the structure of the problem and enable you to make simpler filters overall. That's what I hope to convince you of. But as I said, the Bayesian filters or probabilistic filters are quite popular, so I want to make sure I cover that and give some perspective on how that's related to the things I'm presenting in the course. So let's first talk about non-deterministic filters. Remember, non-deterministic means I'm going to reason about a set of possible states, sets of possible trajectories. Those are the kind of things I'm going to do. When we go to the probabilistic case, it's like the sets have probability mass over them, right? But the sets themselves reveal a lot of information, a lot of good structure. So here's the models that we have. So let's suppose up here I have, I even have something as bad as a non-deterministic sensor. I don't even think I can jump that high. I'm going to try with it. Up here, right? We have the non-deterministic sensor, and so that takes states and goes to the power set of y. So it has a set of possible observations, right? I don't need a laser pointer. Don't worry if somebody's looking for that. No, I like to jump. Keeps me awake. Even I might fall asleep too, right? So I have to jump around a lot. So I want to talk about f of xk uk subset of x. So I'm going to use that notation, right? That's going to be the set of possible states given xk and uk. I have something I'm calling it's I sub ndet. That's non-deterministic information space. It's just a power set of x. Let's see. I gave that notation here, I guess, under bullet number 1. Let's just point that out. There's going to be two of them. There's going to be the non-deterministic one and the probabilistic one. So it's just a power set of x. In other words, it's a collection of sets that I'm going to use for my filter. So I start off with some initial state, which is, call it x1. That's the starting set. So somehow I start off in a set that's a subset of my state space. All right? So that's how the filter starts. We turn it on. We get some initial set. It could be the case that x1 equals x. That means we have no information, right? Maybe we know the initial state, so it's just a single point. There would be a singleton set in that case. So we allow any possibility here. And then I'm going to make a filter for you that looks something like this, where this notation right here, right, this particular, as you see it there, x, k, of a to k, right? This particular notation here just means the set of all possible states given this information. And what is that information? It's exactly this, right? So that's telling me exactly the true set, all possible states that are consistent with that information. Right? It's the largest set that's consistent with that information. So after the very first observation, here's what we should do. If I get the observation y1, I'm going to describe this in an incremental fashion. If we get the observation y1, we just compute this intersection. Does that make sense? Let's take a look at that. So if I say that initially, we're somewhere in x1, right? And then I get a sensor observation immediately. And from my sensor observation, I have some pre-image here like this, right? Does that make sense? So if that's the case, then I can constrain where the state might be to that intersection. Right? So it's very natural, right? So the pre-images come to help us once again, and we take intersections of them. Feels a little bit like triangulation, but things are happening over time. And of course, the triangulation in the sense that I mean, the spatial was from yesterday. So that's all that is. Now we have to figure out how to handle the actions. So this part just handled the observation, the very first observation. I'm going to have to handle the whole thing here now. So up here, I'm going to say generically what to do. You can imagine this as an inductive process if you want. In fact, the base case was given right here. This is how to start, right? This is how to handle the first piece of information. And then I'm going to tell you how to handle all of the information after that, step by step. So let's kind of assume inductively that we've made a way to compute xk, eta k. In other words, we have a way where we've computed this. Right? How do we compute the next one? I want my filter, to go back and remind you, I'm going to drown in notation here a little bit. I want my filter to take this that I have already and take the new two pieces of information and give me the next set of places where I might be. Is that okay? The only difference between eta k and eta k plus 1 is the addition of these, well, will be the addition of these two pieces of information, right, in the next step. So just taking into account these new pieces of information, I have to figure out this set. Any questions about that? Is that okay what I'm describing here? Yes?
I didn't get the difference between this one and the triangulation.
Well, in triangulation, we took the intersection of multiple pre-images because we had an observation from a bunch of sensors. And so we just intersected all of the pre-images to find the consistent state. Right? Now we have prior information, which is where the state might be initially. And we only have one observation from a sensor, which is y1. And so we just take the pre-image of that and say the true state must be still inside of x1 because I know that. That was part of the initial condition. The state has not had a chance to change yet. No time has elapsed. Okay? And then I got this observation, so this is where the state must lie. Is that okay? So now, again, if I make this filter, like this, I'm going to describe that in a couple of slides here that I'm going to go to with a bunch of notation, right? But that's all the basic ideas. This is some set of the states, some subset of the state space. These are the two new pieces of information, action and observation, and I'm going to calculate a new subset of the state space. So that's a kind of filtering process. Here's the idea. So given xk, eta sub k, so assume that that's given, I need to determine xk plus 1, eta k plus 1 using these three pieces of information, just as I said. So how do I do that? Well, the first thing I do is I look at xk plus 1, eta sub k. I'm going to formulate this. That's the first thing I do is I take into account uk. Then I'm going to take into account yk plus 1. So if I take into account uk, here's what I get. I just look at every point here, so every little xk here in this set. I look at every point. Here's little xk. It's very little here, I guess. So sorry, it's hard to see. But I have a little xk, and I look at the one-stage forward projection. So by capital F there, I mean for that to be the one-stage forward projection. That's the set of states you get to when action uk gets applied and you start in state xk. Right? So it looks something like this. I get some set of next possible states given xk and given u. However, I could be anywhere inside of this larger set, so what I do is I apply this capital F function to all of these points in here, and then just take the union of it. Does that seem reasonable? Right? How hard is that to calculate? Well, it depends on the problem, right? Maybe really easy. It could be quite challenging. I bet without too much trouble we could come up with a problem for which it's undecidable. It could be really bad in some really horrible formulations, but I don't think it's just, too difficult for most of the kind of simple geometric instructions that we do. But you know, it could definitely get inefficient. I'm going to show you some very efficient examples of this that I call combinatorial filters, which are special cases of this. But I want you to understand the general formulation first. So that's what we have. And then, if I get it down like that, the way this picture is going to look now, I'll just change it a little bit here. I'll say, suppose now that we have this thing calculated, xk plus 1, given eta k, uk. Right, so now this blob here is exactly this set here, union together, right? Exactly that expression. So if I have that, and then I get the new observation yk plus 1, Don't I just do that? Right? So I used all of my previous information and the current action to calculate this set of possible states, and then I get one more observation. Anytime I get an observation, I just take an intersection using the pre-image of that observation. And that's all. That's all we need for the filter. That's all we need to keep track of the set of possible states. Where did that motion model go? I said there was a motion model that keeps track of how the state changes when you can't observe it. That's in F right here. All right, so F will give me the set of possible next states. Questions? Totally clear or totally unclear? Which way is it? There's going to be some nice, simple geometric kinds of examples of this coming, but that's when we get to the part of combinatorial filters. But I'm going to jump to probabilistic versions of these for a while too, which will have a little more notation even. But I just want to make sure this is a fairly straightforward idea. You know, there's just a set of current states. I apply this F to figure out what the next stage possible states are going to be. And then I get another observation, so I take an intersection because that observation I get is helpful, right? It should be constraining in some way. Each observation should help you a bit, unless it happened to turn out maybe you could be unlucky and maybe this big xk here is a subset of H inverse. Then I guess that means your observation was worthless, right? But usually it helps you quite a bit if you have good sensor. Well, it could have been the case that H here is the dummy sensor. Remember the dummy sensor? Then all of this stuff works, it's just that this is a useless operation every time. If you put the bijective sensor here, what happens? It just goes poof and tells you the state every time. So the intersection here will only have one element, which suggests that there's no need to do all of this ridiculous computation up here, this part of doing this union, because every time you use your sensor, you're going to know exactly where you are. So this formulation is only interesting for the cases in between. In other words, in the sensor lattice, it's for sensors that are in between, which are, I think, the interesting ones.
Sorry?
Yeah.
Why do we not use UK in reverse function H?
Well, H is the sensor model that I defined before. So H is just a mapping that goes like this. It's a sensor mapping. It's one of these virtual sensor models that I gave. And so it just takes the state, the current state, and produces the current observation. So in other words, yk, let's do k plus 1 here. Yk plus 1 is equal to h of x k plus 1. Right? So in other words, if I gave any information about u, it's irrelevant here because once I have x, I have everything I need to predict y, according to the sensor model. So there should not be a u in here because all I need to construct this pre-image, right? Because it only depended, the y only depended on the x. So in order to make this pre-image, you know, this is the relationship here. In order to make this pre-image, all I need is y. Is that helpful? Okay. Anybody else? That's good. I'm glad you're asking questions. That makes me feel good. So please ask some more if you can as we go. Other questions? All right. So, wait, I'm almost going to get to the probabilistic ones. I forgot that I got kind of carried away. I wanted to include this extra case in here, which I really like. Something I developed a bit more recently, so I just put these slides in here a couple of days ago, but I want to include this. These are filters over the entire trajectory space, which I think are interesting to think about. So, hopefully you'll get something out of it. Let's see. So, let's go back to the z space. Remember the z space? That was the state time space, right? So we have state time space. And suppose we have an interval t here, 0 to tf. Tf is called the final time. And then I have something called a complete trajectory, which is a trajectory right here. You see the t there. That's the domain of the trajectory is the entire time interval. That's why I call it complete. And then I have a partial one, which is 0 to t for any t from 0 up to, but not including tf, right? So partial trajectory means it doesn't go all the way. So I want to make that distinction. And then I'll have this, remember I used capital X tilde last time to mean the set of all trajectories. Now I'm going to put a subscript c on it just to be the set of all complete trajectories. I want to do something that reasons about this. I want to make a filter that reasons about this. I think it's kind of nice. I have a couple of slides on this more. But, so suppose we have a set of sensors of the form z goes to y. So in other words, the way those sensors look, h, it goes, let's see, z to y, that means h of x comma t equals y, right? I get some y given x and z, because z is x comma t, correct? Because they made a Cartesian product here. Remember that z is x cross time, right? As it says on the previous slide. All right, so I have that, and then let's make our sensors here be what are perfect timestamps. In other words, I have a bunch of sensors like this kind, which is this one here, all right? But they additionally give exactly what time the measurement was made. So imagine I have a spreadsheet where, you know, I have like an Excel spreadsheet or something if you like, and I have the observation and exactly what time it occurred. And I just have that going down in my rows here. So that's how the information looks that this thing produces. What I want to ask now is, what is the set of possible trajectories? I think it's really interesting to think about. So what's the set of possible trajectories? So I get each y sub I. If the mapping looks like this now, here's the trajectory at time t sub I. And I put time t sub I here again as well, because that's what I need for the arguments to this function h here. I guess I put an h prime there for that one. So this over here now, the regular sensor is h prime. So when I do this, what's the set of possible trajectories? Well, here's something really neat about it. It goes back to this idea of triangulation, and I wanted to show you that because it connects again to triangulations and sensor lattices, if you want. So if I look at the pre-image over the set of all trajectories, I have kind of a picture that illustrates this on the next slide. So in other words, what's the set of complete trajectories here such that I get that observation at time I? Is that all right? What's the set of trajectories so I get that observation at time I? If I can formulate that set of trajectories, all I need to do is intersect them all to make a filter. This is a really weird kind of intermediate filter here. It makes the temporal filter problem look like a spatial filtering problem because it's just a simple triangulation. That's why I'm showing this. I think it's a nice connection. Here's the way the picture looks, and maybe this will be revealing, I hope. So, at some times, here I have T1, T2, and T3, I've got my observations, okay? This is the z-space. The z-space is x cross t, correct? Complete trajectories go from the start to the finish, right? They're complete. That's it. They have to go over the whole interval. And then, these little line segments here are the pre-images of my sensors. And I define my sensors here so that they provide perfect timestamps. That means they're thin and vertical. So if you do that, it's very interesting. So the set of trajectories that are consistent with the observations are just the ones that travel through these intervals here. This one, and that one. So it looks to me like, you ever heard the expression jumping through hoops? You know, like maybe at a dolphin show or something, they put some rings up and the dolphin jumps through or something. That's what the trajectories look like for me. Somebody put some, these are like rings that the trajectory has to jump through. And you put them up and then you look at all the trajectories that go through that. The function has to, the trajectory has to monotonically pass from left to right here. It's a function of time after all, so you cannot zigzag back and forth. And so this nicely characterizes it. So this is an interesting way to view one kind of temporal filter as triangulation. If I get another observation, it just makes another hoop, right? And that further constrains the set of trajectories. But I just think it's a nice way to look at this, and it connects very naturally to the spatial triangulation ideas that we talked about. I could even talk about this as a traveling around in the lattice, like a sensor lattice, but here I can talk about it traveling around in the lattice of history-based sensors, actually, which is all reasoning about the spatial trajectories. There's a lot of interesting structure and interesting stuff there, but probably it's too far away from what we're doing, maybe too complicated, too fast. But I think it's quite interesting, so I wanted to show you that. There's one assumption I have here that's very critical, which is that the exact time is known for these measurements. If I say the time is not precisely known, then these hoops become blobs, and the blobs might possibly overlap, and then it becomes complicated. It doesn't look so nice like this. You might remember that example where we were on the equator of a planet and looking at the light. That was an example where you have blobs in the z-space. Here I did something where you just have nice vertical bars so that it makes hoops to jump through like dolphins. So that's quite interesting. Any questions about that? Can you see then how this temporal filtering is related to the spatial filtering? Because this is just another kind of triangulation. Jumping through the hoops corresponds exactly to this kind of triangulation here, where each one of these sets is a set of possible complete trajectories. Basically, like here, H2 inverse, H tilde 2 inverse Y2 is the set of trajectories that jump through hoop number 2, if you like. You have to recall these hoops that we're jumping through. They're actually jumping through the pre-image, if you want. All right, so hoop number 2 would be this one, so the one I just mentioned. Questions? All right, I'm going to go to Bayesian filters or probabilistic filters, if you like. Yes?
So the sensor model, you assume that you can be based on the position, consider the position, or it can be just like a chemical reaction that over time, the time is going to be included in the sensor model too. Because it's not just a trajectory in some sense, and the position is just the reaction by itself should be included in the sensor model.
The sensor model here only provides, it will measure the state at some time. It's any state space with any transition, it doesn't matter. It's just that I need a sensor that tells me exactly what time it took its measurement.
The only difference is in the case of robotic motion is if you need the time here and there is no motion, it doesn't move by itself, but in the case of chemical reaction, it may change its state over time.
Oh yeah, I'm completely considering cases where the state may change over time. The robots may be moving, they have momentum, right? So robots can be moving, we can be playing pursuit evasion and the evader could be moving. So all of this stuff we consider motions over time. That's quite fine. So that causes the trajectory here, right? This path, that's what's causing the variation in the path, right? It's moving by itself, so to speak. The filter does not control the trajectory, right? The trajectory is just happening and it's being observed. And in the earlier formulation I gave, you might also have the actions as part of your information. So it helps you constrain where you think the state might be going, right? But that's all. Here I didn't even give that. Here I just say there's some hoops to jump through. And if I give a transition model here for this, yeah, you also have to specify what are the possible transitions here in between. Let's suppose for this, maybe a very simple assumption for this, to get an understanding of this, there's different ways to do it, but one nice assumption might be imagine that for the parts in between, we could say that it moves with bounded speed, for example, right? And so that will make some certain types of trajectories possible between H1 and H2 here, between H1 inverse and H2 inverse, as we go through. All right. So, any other questions? Yeah.
Actually, you said that perhaps the time is set even is specified exactly.
Yeah. Well, in this case, the time is specified exactly.
In some cases, you said that.
Yes. In the previous filters, in the non-deterministic filter that I just gave, all you had was the stage, right? Now, if I do these mappings like this from Z to Y, if the time is not precisely specified, then these intervals become blobs. They thicken up, right? And you still might be okay, but I don't completely understand the structure at present. If these blobs become so big that they start overlapping,
Yeah.
it will not make, I think, a pretty triangulation like this.
So if the time is set and change to blocks, doesn't our problem change to probabilistic filter?
I don't see any probabilities yet, no. Because there's been no measure theory imposed on this, right? So we're just reasoning about sets. Other questions? I think very often there's a tendency to jump quickly to the probabilistic models whenever, when there's uncertainty, people want to move to probabilities. And if you noticed, I've handled a lot of uncertainty here so far while talking relatively little about probability. So we've been able to reason a lot about these things because of the many-to-one mappings that we have. This is typically a many-to-one mapping. These sensor mappings we did many-to-one, and we're reasoning about the possibilities here. And I think many times if you immediately go to the probabilities, you lose the ability to see this kind of structure. Because once you put a probability distribution over the whole space, it's hard to see that there's this kind of ambiguity that's very natural. Somebody will say, oh, I have uniform, I have maybe priors that are very diffuse or uniform, and that characterizes my uncertainty. Maybe, but there is something fundamental in these methods, that these mappings are many-to-one, and that's what I want to try to characterize. Other questions? All right, good. I'm glad people are asking. That's good. All right. Bayesian filters. So I want to go back to So this non-deterministic one I just gave here over trajectory space, forget about for a moment and go back to this. Okay, so this is the one I gave a little bit ago, where it calculates. Remember, it calculates x. It starts with xk uk. Sorry, xk eta. Okay, has uk and uk plus 1, and I want to calculate xk plus 1 given eta k plus 1. So that's what I want to do before. I want to make the probabilistic version of that. So what happens if we transform this into the probabilistic setting? It's going to turn out that union gets replaced by something called marginalization in probability, and intersection gets replaced by something called Bayes rule. And Bayes rule does have think about it, Bayes rule feels a lot like intersection, right? You're combining two constraints, and it's giving you a sharper distribution typically, right? And that's what's happening here, right? We do this intersection and we get something sharper. Marginalization usually has the effect of, doesn't always, but it usually has the effect of causing a kind of diffusion, right? Which looks like a loss of information. And that's the way it looks because there's a union here, and that's how it will look when we get to the probabilistic case because of marginalization. So I just want you to think a little bit about that. One interesting case is in these, for these sensorless or near sensorless manipulation problems, you can apply an action and the uncertainty in the state actually reduces in the transition, which is unusual. It's unusual behavior. But for most people, they think of a robot, you command it to go and then it moves in a diffuse way. But if you hit the wall, you actually have better information, right? If you know that you hit the wall, because it's reducing the set of possibilities. So be careful. It doesn't always look diffuse like this. Sometimes it can be constrained, and that's very nice when that happens. So it's very useful. So I just want to point that out. All right, let me jump to probabilistic case, Bayesian filters. So now we have models like this. I have P of yk xk. So that means given the state, there's a distribution over possible observations. Given this model too, this says P of xk plus 1 given xk uk. So this thing here, P of xk plus 1 given xk uk, that's pretty much what we call a stochastic control system, right? Stochastic control system. You have, given the state, given the action, what's the distribution over next states? Or density if these are continuous spaces. So given that stuff, I want to calculate now a filter over all probability distributions. That's what that is. It's a set of all probability distributions or probability densities if you have a continuous space. The initial information state is some prior, which is P of x1. What did I give you before? Remember this diagram over here? I originally put an x1 here for the beginning. The equivalent here in the analog here, in the Bayesian case, is to have some prior distribution, right? Where do you get that from? Most people make it up, right? So let's see. There are ways to make informed priors, but I think a lot of people are just making them up. The filter looks like this now. It says given the previous probability distribution, and now the new two pieces of information, I want to calculate the next probability distribution. Is that all right? Take a look at how close that structure is to the previous case, which was this, right? It says, given the set and the two pieces of information, compute the next set, right? So now in the Bayesian case, it looks very similar, but it has the same filter structure like I gave you, but it says, given the PDF, probability density function, and the new pieces of information, compute the next PDF. So after the first observation, I'm going to start off and do it inductively in the same way. So after the first piece of information, which is y1, you might remember I did an intersection here to compute y1 last time. Now we use Bayes rule. Right, so here's what it says. I want to figure out P of x1 given eta 1. Eta 1 in this case. Eta 1 in this case only includes y1. That's all that's in eta 1. I just have the initial observation. So given that, that's why it's that. So that's equal to that. And now I just figure out what this is by applying Bayes rule. That's just Bayes rule. So I flip x and y like that. And I have to put P of x1 here, right? And P of y, the other part of Bayes rule, is the denominator. This is a marginalized expression for P of y. So now, if I write it that way, then I've used exactly my pieces, right? I've used that thing there to make this, correct? So all I used was my sensor model. Just like all I used was my sensor model in the non-deterministic case. So can you see how the Bayes rule here is exactly the analog of what you got for the non-deterministic case, which was just intersection of sets. Is that okay? All right. A little more probability gore, I guess, not too much really. But so now we assume inductively that we have the current density, and we want to figure out the next density, just like we did with sets. So in the set case, or the non-deterministic case, we figured out the set of possible next states. Now we figure out the probability density function. So for example, I'm given eta k, and now I'm only going to consider uk, and then I'm going to consider yk plus 1. Do you remember how I did it in those two steps for the non-deterministic case? I'm just going to do it exactly that way again. Am I talking at the right rate today, or am I going faster? Okay? Okay, not too bad. All right, just remember to yell at me. So say, slow down. All right, so let's see. So here's how it looks. This, again, can just be written as a kind of marginalization. So here's what we do. We look at the, well, not again, I guess this is the first marginalization I've given here. Before it was a union, right? We had a union in the non-deterministic case. So let's see if we can make sense out of this here. What the heck is going on? So I say I have eta k and uk here. And now what I want to do is I want to marginalize by being given xk. Right? So I say I'm given xk, and then I'm going to sum out xk, marginalization, and I'm going to put this term in here. And eta sub k is given across the whole thing. Right? All right, so I have all of that. And then I notice that once I'm given uk and xk, I have a model of what xk plus 1 is going to be, so I can just use it. It does not depend on eta sub k. Because I was given this as part of the model. This part right here was given as part of the model, right? So I eliminate that. I get this, and I think this is everything I need, right? Because this is the transition model that says how the states change probabilistically. That's this, I guess, right? I didn't need to even go back. And then this was given inductively. So that's all I need. I do marginalization to take into account the action and how the system changed over time, or how the state changed over time. And then to do the next case here, this looks just like the previous one. I have a new observation. It looks just like this, but it just has more notation in it because there's more information being accumulated. So when I get yk plus 1, I try to calculate this, but I'm also given this stuff, eta k and uk. Well, I already calculated what it means to be, what the density is for xk plus 1 given eta k uk. So I'm going to use that. Where the heck does that show up? I think that's here, right? And what is all of this stuff? Did I simplify it on the next slide? Maybe I did. No, I went crazy. I forgot. Okay. So when I get to this one, all of this, it turns out, there's one more level of simplification, which I guess I accidentally cut, which is that my sensor model says P of yk given xk, or P of yk plus 1 given xk plus 1. In other words, I'm given this as part of my model. P of yk plus 1 given xk plus 1. That's the probabilistic sensor model. Instead of being given h, we were given this in the probabilistic case. So if that's the case, once I have x, the assumption of the model is that it's independent of any other information I have. So x, as it's been throughout this course, once I have x, the state, that's enough to reconstruct y, right? In the probabilistic case, it means once I have x, it's enough to infer the probability density over y. So this drops out and this drops out. These both are the same, right? This is a marginalizing expression here. So I meant to delete these as well in one more step. So, so these disappear, and this is the expression, the Bayesian expression for the next PDF. Yep. So that's all we have for this. Is that okay? So what's happening is, based on we start with a prior PDF, probability density function over the state space. We get an observation, gives us another that uses Bayes rule. Then we get an action that uses marginalization. Then we get another observation that uses Bayes rule. So it just keeps alternating. Marginalization, Bayes rule, marginalization, Bayes rule. The non-deterministic filter kept alternating. It said intersection union, intersection union. So it's just changing in the same way here. It just looks kind of fancy with all the probabilities and such, and has mysterious conditional independence and other things like that, but it's the same basic idea. Other questions about that? Sorry about not deleting these. These should be gone in the next. Should be another equals here, and then yeah, maybe it's right here. Trust me, it's here. You guys have to look like it. All right. It turns out that it's quite complicated to compute these filters because if I have to reason over continuous spaces, so if my state space is continuous here, what happens to these sums? What do they turn into? Integrals, right? If you have measure theory, you can just say they're all integrals. They're all just a Lebesgue integral if you want. But you know, so it doesn't really matter in some sense. I kind of forgot that I was doing discrete ones here, but in general, you have integrals, and well, guess what? You might find yourself doing a lot of high-dimensional integrals over configuration spaces. Does that sound like fun? No, probably not, right? If you know anything about integration. Usually when you take a class on calculus, they show you all of the stuff that works nicely, and then you do them as homework problems. And then when you start doing research, you realize that almost nothing can be integrated, right? Very nicely, right? So they kind of lead you down a nice path. Did you know that? Let me show you a good one. I'll go off. I'll go off on a small tangent here, and then we'll take a break. So let's see here. Let's take a circle. That's not very clear. Let me take a circle. Oh, those are new ones there? Okay. Thank you. Let's take a circle. Let's keep trying. Let's take a circle. Just like in the movies, you know, they have to keep doing another take. Take 3. Okay. That's not a very good circle, but let's suppose it is. It has radius r, so the area is equal to what? I don't remember these things. Pi r squared? Pi r squared. R squared. And the perimeter or circumference is what? 2 pi r. So the circumference is 2 pi r. Okay, very good. Now, I make an ellipse with major and minor axes A and B. All right? What's the area? Pi AB? And that's really neat because when you get the circle, it looks like that, right? And because the circle is a special kind, it will look wonderful. Pi AB. Now, what's the circumference or the perimeter of that? It's a nasty integral, isn't it great? So I just thought it's one of the first things I discovered. Like, whoa, wait a minute. You know, looks like it should be something like 2 pi, I don't know, maybe square root of AB or something, so I can get the dimensions right, you know. But no, it doesn't work. Anyway, it's just very funny. You know, it didn't take me long in research to start. I needed to compute some turned out integrals. I needed to compute these surface areas of ellipsoids. And I got all the way down to dimension 2 and realized I still don't know the answer. And I thought that was pretty funny. And then I looked at one of my handbooks on mathematics for engineers or something, and somewhere in there it said this one was approximately equal to something. And I'm like, why would it say approximately equal? And it was a great mystery to me. So it's the elliptic integral that you need to evaluate, right? And you can do trig substitution methods to make the elliptical integral give you that if you want to do it by integration, but the trig substitution does not work for ellipses. Anyway, just kind of a little bit of a tangent. I'll take a break now.